Okay, awesome. Nice to meet you guys. My name is Shreya Nallapati. Thank you, Tali, for that amazing introduction. I'll just get right into my background information, more about Neveragaintech, because I'm sure that's a lot of the reason why people are here today. And then I'll also end up talking about really what the main focus of the talk is today, which is improving your ML model, especially when you have imperfect data sets. I think that mass shooting data is probably the epitome of having an imperfect data set. So I'll talk about some of the techniques that my team and I are employing right now in order to kind of mitigate some of the, pitfalls of having an imperfect data set, but also some mathematical concepts in general, because I am a math major here. So so I basically created Neveragaintech after the Parkland shooting in 2018. I think that it was a very, very dire situation, and my generation is known as the mass shooting generation, right? We grew up with Columbine, Aurora, and all these devastating events. But the Parkland shooting was my call to action, because after watching the student activists come out of there, I wanted to see how I can contribute as a technologist, because that's primarily my expertise, my area of expertise. So I really thought, why are we using such powerful machine learning models, to post meaningful thoughts, meaningless thoughts and condolences, when we can actually be using that to kind of understand the fundamental anatomies of mass shootings and how they occur and how they materialize. And so this led me to create Neveragaintech. Primarily what we're doing in terms of what we're actually achieving on the machine learning aspect is we have already built out a decision tree classifier with a corpus of mid-80s range accuracies and predictability based on the factor. So basically in our R model, we created a decision tree. It's not really random forest, and I'll get into why we don't like random forest here, and determining the correlations between time of day, location, relationship of shooter, relationship to the incident location, and a multitude of other factors in predicting the occurrence of an event. More importantly, and I guess this is probably the most enthralling aspect of this talk, is we built out a classifier on a social media data set to categorize a given social media post as being a hoax or a real threat based on a regression analysis of past posts. Try saying that 10 times. But basically, what we did is we looked into all the past manifestos that every shooter posted or tended to post. And sometimes they occurred on forums like 8chan and Reddit. Sometimes they actually occurred on physical pieces of paper. And we determined what distinguishes a hoax threat from a real threat. And we basically built a specialized lexicon of the terms and phrases that perpetrators of real tangible mass shooters use, and what really distinguishes a hoax. I'll give you an example. A hoax is something like what we discovered the most common attributes of a hoax would be, I'm going to shoot up the school tomorrow, or don't come to school tomorrow. Those were phrases that were really associated with people who posted these things as for attention or for jokes. And we also realized that something that was more indicative of a real threat were things that had manifestos, people that use very extremist-based hate language, and we were able to distill it down, and we currently have an 88.46% raw accuracy on a repository of 427 points. So it's good, but it's not good enough. So now I'll talk about why we need to improve and what the motivation for this talk is. Because again, there has been a real limitation with accessing mass shooting data. It all happened when the NRA basically prevented the CDC from conducting mass shooting related research, and it was part of a rider in a bill called the Dickey Amendment. So for about 20 to 30 years, basically the CDC or any other governmental organization was stalled from conducting research in the mass shooting area. But now for the first time ever, after years and years of activism, they started to donate, a base of $5 million for research. So this gives us a lot of potential to look into tangible applications of supervised ML. So what is my motivation for this talk? So going back to the topic of there are some undeniable restraints when it comes to mass shooting data. There's actually a very small number of positive events. So in the grand schema of when we have data for a machine learning model, the actual number of true positive events as it relates to mass shootings is sometimes few and sparse, despite what media says. So media tends to sensationalize school shootings when they occur, but when you actually look at it in the context of a timeline, there are actually very few school shootings that occur and very few mass shootings that occur. And even if they do occur, it's never actually brought to light. It doesn't actually occur. It doesn't actually show up in social media as much as it does is if a lone wolf shooter, decided to, kill a lot of his own friends or students. So that's why there are very few positive events to actually intercalate into a data set and kind of classify as being a positive or negative. Secondly, there's really no way to properly identify what a negative can be classified as. There's a black box around what a thwarted mass shooting attempt looks like. So going back to my social media example and what we're doing with the social media repository, we as a team, we really struggled with identifying what does a zero post look like? What does a hoax post look like? Does it look, is it classified as people who post about joking about mass shootings? Does it look like someone who thought about committing a mass shooting but didn't actually go through with it? And what about the injuries that only result, what about the events that only result in injuries and not deaths? So there was a very, very gray area in terms of what we could set as a binary indication of what is a zero event, where it's like a thwarted mass shooting attempt, versus one. One is where the shooter executes it and goes through with it and it has considerable impact. So that was one of the big things. And additionally, I know that most times when we think about machine learning and AI, we tend to think of neural networks. I think that's the hot new topic in the trend right now. But using machine learning to mass shootings, for mass shootings is considerably harder than something like using neural networks to identify malignant tumors, which is really one of the most prominent examples right now. Because in that situation, cancer data scientists can actually determine, they have a good idea of what a benign image looks like. It's pretty delineated clearly. But here it isn't. And also they have a big enough repository of what malignant tumors look like, so it's easy for a machine learning model to distinguish between malignant and benign. This isn't the case here. This is a very social problem. But what we can do is we're starting to attempt and vectorize some of the data that goes along with mass shootings in order to get a bigger, clearer picture. Another problem that we have with data is that the dimensionality is too broad. For every past mass shooting, there are just so many factors to consider when we're putting it into a data set. The time of day, the type of gun, the history of mental illness, what type of mental illness, which form the threat was posted to, if a threat was even made beforehand, the demographic, the age of the perpetrator, the age of the victims. So there is so many features that go along with each and every individual past shooting event. So it's really up to the scientists to determine what features are the most prominent when building out these models. And finally, past events create a lot of spurious signal. So I will mention this time and time again in my talk. This is probably the biggest takeaway here. It's hard to make generalizations off of events that occurred in the past. Taking Columbine, a very prominent example, into consideration, the specific details that contributed to Columbine cannot be replicated in the future. It is impossible. So it is really hard to use regression analysis to say, well, the next mass shooting looks like this, this, and this, because the things that contributed to Columbine won't contribute to the next mass shooting. There are similarities and we're trying to capitalize off of that. But the biggest thing is the model that we create, any model that we create actually will overfit for every single shooting that occurs, because there's just so much variety in between. So these are some of the biggest kind of like problems that we had and we continue to have with creating a machine learning model off of mass shooting data. It's all distilled down to it's hard to make generalizations. With that in mind, what mathematical models can we use with imperfect data sets? So basically, this talk can be distilled into mitigation techniques for overfitting. Overfitting is a really big problem in machine learning models. Whether or not you use it for mass shootings or not, it's probably one of the biggest problems that a supervised ML model will face in its duration. Additionally, the models that, the techniques that I was talking about for overfitting are primarily distilled down to bagging and cross-validation. And also, I'll be talking about feature selection through one-hot encoding and regularization techniques. So let's begin with feature representation and distilling it into sparse arrays. Okay, so most machine learning models require numerical data. When exploring social media posts about mass shootings, it's hard to classify sentences and phrases without distilling it into a binary array, or like an array of 0 and 1s. Models are not built to detect the words gun, shoot, school, and all these expletives in the broader context of the English lexicon. So feature engineering, specifically by representing categorical values in sparse arrays of 0s and 1s, is proven to be an effective mitigation method. So feature engineering in general can be used to generate missing values, definitely not in this case because you can't generate a mass shooting value by taking averages. Can't create a mass shooting when there wasn't one. It can be used to detect outliers in data, it can normalize skewed data, and it can split data structures, for example, splitting characters from strings. So in our mass shooting data, there's there's a really prominent library that I recommend that everyone look at called the Stanford Mass Shooting Library. It has around 400 instances in it, I think. Well, basically, we realized then when they went back and categorized the type of firearm that is used, there are different types of assault rifle. There's AR-15, AK-47, and then you go into pistol. There's 9mm pistols. You know, there's so much in one little representation of what the weapon was used. So we really thought that feature engineering was helpful in extricating the characters from the strings. So taking AK, AR, and taking the numbers out of it to get a generalized picture of the weapon that was used. Because otherwise, you can just go back into that overfitting thing where you just keep going after, okay, well, anyone who uses, all mass shootings are committed with this specific weapon. It's not like that. Secondly, in text representation, one-hot encoding, let me just go to them. One-hot encoding is the most prominent technique. So for each word appearing in a set of examples, it creates a feature that is 1 if the word appeared in the particular example and 0 otherwise, and builds out an array of sparse binary values. For example, if I have the text that we commonly see, don't come to school tomorrow, or I'm going to shoot up the school tomorrow, sorry. Then basically what the one-hot encoding does is, we already identified school, shoot, and like tomorrow as words, so it'll be 100100, because it puts in ones for when that feature actually occurred in the text. Again, this is the foundation for most of the text vectorizers. So going back to the social media dataset model that I previously mentioned, we used TF-IDF and a basic count vectorizer to kind of distill text into numerical values. So a pitfall that we run into with one-hot encoding is that there actually exists a high correlation between features. And sometimes one independent variable can be used to predict the others. And it also may result in voiding any statistical conclusions, but that can be mitigated through a technique called principal component analysis. It basically kind of uses linear algebra on a very, very, like, the smallest term that I can use about it. So basically, just to repeat, one of the biggest things that we use for feature engineering with a data set that is already so, variegated, is we basically used one-hot encoding to distill each text into a 1 or a 0, and then from there we were able to build a multinomial naive Bayesian classifier out of that. But the biggest thing here is that feature engineering is especially important for imperfect data sets, because it allows you to, make everything consolidated, especially in areas where they're not. So feature engineering is a really big thing that I'll keep focusing on throughout this talk. And here you have an example of one-hot encoding. So, and it's not necessarily, so there's 2 distinctions here. There's label encoding, which will put like apple, chicken, and broccoli as 1, 2, and 3. But here, one-hot encoding, again, distills it into binary values. So apple has apple, but it doesn't have chicken or broccoli. Chicken has chicken, but it doesn't have apple or broccoli. And broccoli has broccoli, but not apple or chicken. So it makes it easier for many binary classification models. Ooh, now we're talking about overfitting, my favorite thing. So basically in this roadmap so far, we've kind of dipped our toe into the ways to clean up data and present it in the most compatible format for a model. I think I have to be, it's a very cursory introduction to what one-hot encoding is, but it's specifically relevant to what my model does, because again, with so much text and so many manifestos and so many hoaxes to comb through, there's nothing better than just making it very numerical, because otherwise you can get caught up in the, there's so many, there's so many classifications. Okay, so now overfitting. This is super, super, super important for any machine learning model, because especially when it comes to mass shooting data, we are talking about a very limited data set. So most supervised ML models have thousands and thousands of data, sometimes going into 100,000s. But here we are limited. We only have 500 instances from 1990 to 2016 if we define a mass shooting as a place where 4 or more people are injured or killed. There's not that many out there. So with such a limited data set, how can we actually bring out important, very important, deep generalizations out of this? And that's when overfitting occurs. So basically overfitting occurs when the model trains on the data too well, and it fails to make generalizable predictions because it is too adapted to the specifics of the particular set of examples used to train it. So I previously mentioned the few positives, ill-defined negative classes, but now I'll talk about spurious signaling. So back when I identified what were the primary things that like makes the mass shooting data set an imperfect data set, I talked about these things, but I kind of generally mentioned spurious signaling. So going back to Columbine, so we have Columbine and the features surrounding it, right? We have the diaries, the demographic of the shooter, even down to the exact video games that they played, right? Overfitting here is a problem because the model is so attuned to these few true positive events that it fails to make generalizations for the future. Our biggest goal in developing these machine learning algorithms is to make generalizations for the future, especially in regression and classification environments. So here's where we introduce a technique called cross-validation. It is basically a sampling strategy that allows ML practitioners to utilize more of their sample set for training. In other circumstances, we would be able to use, if I had a large data set per se, I'd be able to do a 60-40 training testing split and still have 1/3 of our data left for us to develop specialized hyperparameters. But cross-validation takes in those same parameters of small data, but allows partitions for the model to learn more and iterate more times over, which is in k-fold cross-validation. So you are making 100% use of smaller subspace. It is not an accuracy estimate. I think most people think that cross-validation is another accuracy gauge like AUC, lift, or just a raw accuracy confusion matrix. It's not. It's more of a methodology for robust model selection and estimation of model performance. So overfitting is really meant, cross-validation is really meant to tackle the problem of high variance. So most people here probably know about the bias variance trade-off, right? When you have high variance, you have low bias, vice versa. But really, cross-validation as a concept, as a technique and methodology, is really meant to tackle variance, not bias. And so variance really is a type of error that occurs when the model is too sensitive to the smallest of fluctuations in the data set. For example, if I'm looking at, and I would never recommend doing this because it's like the minority report, but if I wanted to classify potential mass shooters, overfitting of past instances would say anybody with a mental health disorder is a potential mass shooter. You don't want to do that. Or anybody who was born at this time and this age and has this demographic and this family background is a mass shooter. That is what overfitting essentially is in this context. But what we want to do is take every method possible to try and prevent that. So now we'll be talking about k-fold cross-validation, and this is probably the most prominent example of cross-validation that you'll come across, because it's either this or stratified, which I'll continue on the next slide. So basically, what does k-fold cross-validation do? It repeatedly uses k-1 folds to train and make out of sample predictions on the left out fold. So it uses k, so there's like k represents the total data set, right? So it does k-1 to train and leaves the leftover to actually test. And so the benefit of this approach is that the respective training sets are comparatively large, and you also have out sample predictions on the entire data set, allowing for a robust estimate of the true generalization performance. So one commonly used performance metric for regression is R-squared. So for the mathematicians in the room, you guys know what R-squared is, right? So with cross-validation, we can calculate the R-squared for all of the different hyperparameter settings and modeling choices and pick the best in terms of expected generalization performance, highest R-squared. I won't go into too much R-squared, but just think of it as a mean squared MSE derivative, mean squared error derivative. It's just basically meant to understand how well your model is performing. And so we must note here that there is no replacement of data in k-fold cross-validation. Other cross-validation techniques allow replacement, but here there's none. So if you use some data to do split 2, you can't use that same data to do split 3 and split 4 and split 5. And then additionally, back to the context of mass shooting data that we keep talking about, this is especially beneficial in classification environments when utilizing metrics such as area under curve, raw accuracy, and lift. So how exactly do we determine what k should be? Is it this next slide? Yes. So not to make an overbearing generalization here, but in most regression and classifier instances, it has been empirically proven that the best number of folds is between 5 and 10. And anything bigger than 20 requires a lot of computational power, which in a lot of instances we're limited on. So which is not tangible for most practitioners. So anytime you're doing logistic regression and you have a good data set and you have good model performance, you usually tend to put your K between 5 and 10. It's actually proven, and if you guys have ever participated in Kaggle competitions on machine learning, usually they recommend that you use 10 folds to do that, and I'll explain why in just a second. So now that you see this slide right here, right? So basically there's one thing that I recommend any ML practitioner in the world to read multiple times over and over. This is like the holy grail of the best research, the best paper on cross-validation. So it's called A Study of Cross-Validation in Bootstrap for Accuracy Estimation and Model Selection. It's by Rohan Kohavi at who is a data scientist at Stanford. So basically, the reason why 10 or any number between 5 and 10 is the most optimal number for folds is because he basically conducted 500,000 runs of C4.5, it's a model, and naive Bayesian modules, and has empirically proven that the bias is the least between 10 and 20. So you can see that right here. At 10 and 20, the accuracy and the bias kind of tends to plateau out, which is why we choose the folds to be right in that area. So again, to reiterate, bias is the simplification of assumptions to make the prediction easier to estimate. And so each machine learning model tends to always have some level or variance or variety of bias. Bias and variance, again, is the tangible amount of like how off we are from the actual prediction estimate. And so another really important thing to know when we're talking about K-fold cross-validation. The reason why smaller data sets typically require a larger number of folds is because smaller data sets require a larger percentage of the training data to operate on. And this larger percentage of training data can be divided into these specific number of folds. So if you have a large enough data set, going into the thousands and hundreds of thousands, you can go back to the 60-40 training testing split, and you could still have, and you can just have a little, like a couple of folds. I've seen people do, create the number of folds as low as 2, but when you have a smaller data set like mine, you want to have more folds so that each time the whatever model that you choose has enough to operate off of. So now that we've looked at K-fold, I know I went really fast. Does anyone have questions about K-fold cross-validation? Yes.
Yeah, when you say more folds, does that mean more than 10 or just as close to 10 as you can?
As close to 10 as possible. I think the reason why is if you go above that 10 to 15, more like 15 to 20, it just requires so much computational power. And unless you have like NVIDIA GPU, it's going to be really hard for you to be able to do that and still have your model running. So it again depends on the environment, but unless you don't want to use computational power, stick between the 5, 10, 15 range.
Thank you.
Any other questions? Please let me know if I'm talking too fast. I tend to do that. Awesome. So now we're going to be looking at stratified cross-validation. And this is a much more powerful than K-fold cross-validation. So what is stratified cross-validation? So basically, it really is here to tackle unbalanced data sets. So this is where you have where you have like a really big difference between your minority sample and your overall sample. Okay, and so the way we tackle the problem of unbalanced classes, especially we really have just to reiterate, with the social media post repository in regards to mass shootings, the biggest problem that my team and I ran into was a problem with unbalanced classes, because again, the amount of hoaxes that are posted at any given time on a social media forum outweigh largely the number of true things that actually materialize, right? For example, in school, they have so many students on Snapchat and Instagram saying like, don't come to school tomorrow as an unfortunate joke. But how can you actually extricate the ones, the people who have an actual intent? This creates a very, very unbalanced class. And so in our probable versus improbable threat consolidation, if I remember correctly, the ratio between 1s and 0s was 2 to 8. So for every 2 instances of a 1 or a real mass shooting threat, we had 8 hoaxes. So that's a very imbalanced data set. And so the goal of stratified cross-validation is to ensure a more or less constant base rate, right? So we want a constant percentage of positives across all the folds and avoid having only negatives in one fold. Because when you're conducting K-fold cross-validation, it's really possible that in your split, you can only have negative data points, only have positive data points. And this basically nullifies your entire statistical conclusion that you come up with. So that's why we have stratified k-fold, which basically balances out the classes in each split. So again, stratification, it's the arrangement of each fold so it is representative of the classes in the data set with respect to the target variable. So each fold has the same base rate. If that's one thing that you take away from a stratified CV, it's that each fold has the same base rate. And also, moreover, this basically means that every fold has the same number of the minority class. Okay, so on a more technical note, you can see right here how k-fold cross-validation tentatively looks like in a Python environment. So you can see how it's a lot to process. Basically, you have like a matrix and you make sure that, for example, here we have a 1:10 class ratio. So we're basically making sure that every train and test split has this exact same number, and it's very hard to make it an easier, more consolidated process. So the trade-off between k-fold and stratified k-fold is that stratified k-fold takes a lot longer in order to make sure that each train and test split in this matrix has the exact number that you identified as your proportion. Whereas k-fold, you can just kind of run, there's like a very simple Python command that just like k_fold. Here you have to kind of delineate it properly. But the best practice, again, in light of like Kaggle competitions or anytime you're doing a machine learning model, it's the best practice is to split the positive and negatives between training and testing equally, and then proceed to preserve the class ratio for the stratified folds. So yeah, so that's basically stratified cross-validation. Again, it's really used to mitigate overfitting, because when you have a smaller data set, like in this machine learning, in this mass shooting model that I previously mentioned, it's so easy to be so caught up in the past events that it's hard to make a generalization for the future. But through these cross-validation methods that I previously mentioned, you're allowing for more of the data set to be used in training instead of testing. And you can develop specialized hyperparameters out of these training models, out of using these more of the training set. And what this allows you to do is make better generalizations for the future. Otherwise, if you're doing 60-40 on a small data set, you're not using the entirety of the data that you can be using, making it a really, really shitty conclusion for your model. Now we'll be talking about mitigating overfitting by reducing model complexities. So a lot of times in L1, in logistic regression environments, the most common thing that you'll see every ML practitioner do is with LR, logistic regression, is they'll have 10-fold stratified cross-validation, combining it with penalties. Has anyone heard of like what the L1, L2 penalties are here? Oh God, it's okay. I'll try to explain it as best as I can. So let's look at what overfitting looks like mathematically. So mathematically, overfitting is basically described as a function that has multiple parameters or coefficients. So when you have linear regression, you have theta x1 plus theta x2 as mathematically as possible. But for a more complex model, you have theta x1 plus theta x2 squared plus theta x3 cubed plus theta x4, like, you know, to the power of 4, right? And so overfitting is, if I can just draw this up here. Overfitting is taking into consideration all of these separate parameters. So say you have a function that looks like this. You have this parameter, this parameter, this parameter, this parameter, and the coefficients basically overfitting basically looks like this. So what your machine learning model is trying to do is it's trying to adapt to each different separate coefficient and parameter, and it happens when you have more complex functions to look at. Whereas if you have a linear regression model with theta x1 plus theta x2, it's easier to develop something that will fit this line than it does to fit this line, right? And so that's kind of what it's distilled down to. Basically, overfitting is where your model is trying to basically be parameterized to all these ups and downs of these curves, whereas for a linear regression model, it's just like, how do I fit a line to match this? It's easy as like putting it over it. So that's on a very, very, very simple level what overfitting looks like mathematically. And so basically, regularization, also known as L1, L2, or lasso or ridge regressions, basically constrains the parameter and makes it as close to 0 as possible. So what you're trying to do is you're trying to mitigate these like fluctuations and make them more into a function instead of having your machine learning model try to account for every up and down of this curve, right? And so So basically loss functions can be modeled as basic. I put up a function here, I don't really like it, so let me just rewrite this down. Sorry, give me 1 second. The logistic regression function, or the function for the loss function for a logistic regression model basically looks like this. You have a sigma I is equal to 1 to n, yi minus x prime I b hat squared, plus lambda sigma j is equal to 1 to m b j with a hat. So this is what the loss function looks like for a logistic regression model. You can see right here that say you have L right here defined as W minus H. It basically describes the weight, is known as the weight describing the overfitting. And so the L1 regularization, again, this is more mathematical. You guys don't need to pay too much attention to this. It counts for the shift, it counts for the exact shift from the W, and that is known as the lambda. So this right here is the shift that the regularization accounts for in order to make this, and it tries to make this as close to 0 as possible. That's what we're doing with regularization and penalties. So whereas in ridge regression, the betas or the parameters will become infinitesimally smaller, they'll never actually achieve 0. Whereas in lasso regression, it will ensure that the parameters go to 0. So again, we're trying to minimize this lambda as much as possible so we can have a nice function to kind of draw and fit on. So again, just to reiterate, L1 penalties with tenfold cross-validation are probably the most effective ways to ensure best model performance, especially during Kaggle competitions. So anytime you have a Kaggle competition, these are kind of the parameters. I don't want to make an overarching generalization, but that's kind of what you do. And so yeah, so basically, again, to get overfitting, what I was trying to do right here is when you have a high bias and underfits, this is the optimal curve that you're looking for when it comes to overfitting. If you have high variance, that means there's so many fluctuations due to the parameters. And what you want to do is mitigate those fluctuations as much as possible so your model can fit it just right. So anytime that you're thinking about overfitting from a mathematical perspective, always you want to ensure that the model comes as close to this in the middle as possible because you don't want underfitting or overfitting. Finally, I'll be talking a little bit about mitigating overfitting by aggregating models, also known as bagging or bootstrap aggregating. So this is a very, very effective machine learning technique when you have a lot of weak learners and you want to kind of combine them all to get the best measure of a predictive performance. So what is ensembling or aggregating at its core? Basically, what it is each classifier trains on different randomized subsets of the data, and instead of training on the same training data in mathematical environments. And so what it really is a selected combination of different classifiers distilled into one big classifier that can provide us with the best generalization performance. Majority voting is usually used in these in ensembling. It means that you basically select a label that has been predicted by most of the classifiers. So if I put in SVM, support vector machines, and I have a decision tree model, and I have like 2 logistic regression models and 1 classifier model, what a majority voting would do is it will take out the most predicted label predicted by all of these classifiers, and it's going to use that for future generalization. And so the best example of ensembling would be ensembling between classifiers that are like decision trees naive Bayes. Or if you want to explore it from a deep learning perspective, I don't know if anyone here is interested in deep learning. It basically is, there's basically snapshot ensembling for photo classification. So it's not just something that's specifically constrained to like supervised ML. And so what you're doing here is you're aggregating the most frequent prediction across all the classifiers, and it's also known as statistical mode, so that the error rate of the ensemble is lower than the individual classifiers. So say my error rate for my SVM is something, it's pretty, I wouldn't say like, yeah, like let's say it's like 51.2%. We've known that like by aggregating the most frequent prediction, there's a Python script that basically does that. It'll drastically lower it just enough so that you can classify it as having good prediction performance. And it is optimal really when the base classifiers work only marginally better than random guessing. So if you already have the perfect strong learning model, there's no need to do an ensemble. It's for when all of these things are so weak that you need to combine them together to get the best prediction and best through majority voting. So then what exactly is bootstrap aggregating? So bootstrap is a sampling process. Aggregating is the thing that pulls everything together. It's also known as bagging. Basically what it is each time the classifier trains on different randomized subsets of the data instead of the same training data. So usually in ensembling, you have the same data that is distributed across all classifiers. This time it's not like that. In bootstrap aggregating specifically, each different classifier works on a different randomized part of the data. And additionally, replacement is allowed here. So what that means is that there's repetition among the partitions. So basically, if one data set you can see similarities between data sets because they're working on randomized subsets, but there's replacement. The biggest distinction here is that about bagging is it runs several strong learners in parallel, which is the biggest mitigation factor for overfitting. So another ensembling model that people talk a lot about is boosting. Boosting is running weak learners in sequence, whereas bagging is running several strong learners in parallel. And this is the best mitigation factor for overfitting. So now, has anyone heard of random forest here? It's a random forest, right? Oof. I don't like it at all, but that's just my personal bias. So random forest is basically a specialized case of bagging where each split contains a random feature. So random forest is basically consolidating all these decision trees together and trying to make a generalization off of it. There's a reason why it's called the most flexible model is because it pays attention to each different split and it tries to make a generalization out of it, and it's impossible if you have too many variegated splits. And so the biggest distinction, however, is that each individual tree or each individual decision tree is equipped with a random subset of features. So bagging means that each tree would be provided with a full set of features. In random forest, the individual tree is equipped with a different feature to be training off of, different split, basically. And they both end up aggregating the results of the individual trees. So on the subject of random forest, as I previously iterated, it is one of the most notorious algorithms out there for producing overfitting because it's so flexible to each individual tree. Random forest groups all of these like splitted nodes together, making it even harder to get an effective generalization. So it's not recommended for smaller data sets. So when my team and I were looking at the best algorithms to use for a small data set, we originally thought about random forest because it's something that a lot of people use in unsupervised ML when you don't have a generalization in your data already. But then we realized that it's not good because it has so much flexibility that it will again contribute to the problem of, for example, when we have the classifying a potential mass shooter instance, it can basically say everyone that has this mental illness that had this background, that was an ex-veteran, blah blah blah. It'll try to create generalizations like that, and that's not effective for the future. And so basically, and there's a mathematical formula. Again, as a math major, I can go all about it, but basically it's a basic combination where n choose k is the binomial coefficient, and E carrier is the error rate of a single classifier. You combine that together and you get the error rate of the ensemble, and this will be collectively better than the error rate of a single classifier. So this is the mathematical formula behind ensembling. It's n choose k, and it's basically, it kind of capitalizes off of the binomial coefficient. But the overall takeaway is that the error rate of an ensemble of weak learners is better than the error rate of a single classifier or a single weak learner. And so I know I kind of skidded through that, but don't worry, I have a lot more to talk about. So basically, the future work, and so basically what we did is we covered how with small data sets, going back to the mass shooting problem, there's a real big problem of overfitting. So we talked about overfitting in these different lenses. We talked about overfitting and mitigating that through cross-validation, and specifically stratified k-fold and k-fold cross-validation. We also talked about mitigating overfitting through feature selection and feature engineering, and that's when we talked about the regularization and penalties, right? But the final thing that we really wanted to touch on is and the most important thing is using bootstrap aggregating or ensembling of different classifiers to come up with a better estimation of our predictive performance. So when it comes down to it, especially when you have these different machine learning environments and you're using unsupervised and supervised ML, using a combination of all of them instead of just relying on one gives you a better sense of generalization for the future, because that's what we're trying to do with mass shooting instances. We're trying to use all these past information to create a better idea or picture of what it would look like in the future. So when you're looking at mass shooting data and you're trying to apply machine learning to it, it does seem like a very daunting task because mass shootings are so randomized, B, they're so social. It's not really something that you can make quantitative, right? Which is what you usually use for machine learning models. And C, you really want to make sure that you're not identifying false positives, because the last thing you want to do is classify a post as being indicative of a mass shooting when someone's joking, or even more so using this specific set of factors to say this person looks like a potential mass shooter when they're not. And that's really a big problem that other AI companies are doing, and it's creating a lot of privacy concerns, ethical concerns in this field. So what my project really is doing, what Neveragaintech is doing, is reviewing the landscape in a drastically different way. We are putting our efforts behind a new data collection method that doesn't inherently infringe on privacy. Going back to the big subject of privacy here, the last thing we want to do is crawl through people's personal social media profiles and try to get a picture of like what they look like and what they're trying to do. Instead, what we're trying to do is collect data from publicly made posts, publicly made profiles. This is why we focus on Reddit and 8chan, anonymized fringe media forums, to look at potential mass shooting threats, because in 2019 itself, three of the biggest mass shootings that we've kind of faced in this decade, the El Paso shooting, the Christchurch shooting, and the Ciabatta Poway shooting, they were all made on these forums. Specifically, even more in specifics, all these manifestos that were posted, I don't know if you guys know the details, it generated a lot of conversation and a lot of copycats that didn't end up going through. But if we pay attention to those forums as a way to collect data, you're not infringing on privacy because they're anonymized. That's the biggest thing about 8chan and all the chans in Reddit, they're anonymized. And B, they're really focusing on extremist-based environments. So you're not looking through all the Instagram profiles and Snapchat profiles of everybody who goes to a specific school. You're really looking at the people who tend to populate on these fringe areas and trying to determine, hey, are there correlations between the manifesto that was posted and the people who are making manifestos to copy that, or the people who are using the same extremist-based language to target different groups. So that's why really the biggest thing that my project is doing is we're looking at data collection in a way that doesn't infringe privacy on the forums that matter the most. Because the last thing I want to do is go through your Facebook profile and say, hey, this, and this about you. You really want to focus on the outliers. Secondly, we're really determining the best mathematical models that end of the day reduce the feature space by smarter feature generation. A lot of ML startups in this area of like trying to detect and prevent school shootings, they have a very, very limited definition of the math behind this. I think the biggest reason why I became a math major in the first place is because all machine learning is inherently based on math. So without a good definition of the formulas and everything, and if you keep going on to Python and downloading whatever package there is, you don't really have a good perception about what exactly your model is doing. In AI, there's a really big black box. Specifically, when people talk about throwing a neural network at a problem, they don't even know half the time what the different layers mean, what exactly it's trying to do, or how it even classifies a specific image, right? And so without a good definition and good distillation of what the mathematical procedures are behind machine learning models, it's really impossible to get effective conclusions. So that's kind of what we're doing too. Finally, I know before I kind of emphasized the importance of unsupervised and supervised machine learning in these environments, but we can't really completely deny deep learning too. So again, I know a lot of other startups in this area are kind of using neural networks to identify when someone's holding a gun in their hands, right? There comes a lot of problems with that because there's not enough data. How many people are actually walking through hallways with an assault rifle in their hand, and that's ready for classification. Here, we're really looking at the most tangible instances. So understanding how mass shootings materialize in the first place by looking at social media threats, by looking at what combination of factors are the most generalized across all these specific instances. Not going and looking and trying to characterize a mass shooter based on what one Columbine profile looked like, but what is the commonalities through these regression and classification models between Columbine, anything in 1990s too, because that's when mass shootings actually started to first materialize, not in 1999, right? And finding generalizations that we can make to predict effectively for the future. And so right now the team is, for all the deep learning geeks right here, We're using word-to-vec and dynamic embeddings, specifically word movers distance, on these posts that contain a plethora of information. So you know how manifestos that sometimes these shooters post are down to 30 to 50 pages of pure jargon, right? So what we're trying to do is, okay, I can't manually go through that. Even a supervised ML model can't go through that and extricate all the important things. So we're going to start shifting to deep learning as a focus. So using embeddings to determine the commonalities between these manifestos, these ideologies really, because there's a lot more information contained when you actually look into the Columbine diaries, or if you look into the Chapata Poway shooters manifesto, there's a lot more information contained there. And most of the media tends to just specifically generalize that, oh, it's extremist hate-based ideology. No, there's a lot of information there that kind of compels us to understand why a specific shooter did what they did. And so we're using deep learning, specifically word-to-vec word embeddings, to determine the correlations between ideologies through these manifestos or long posts that are doing it. So next time, anytime you go back and research a mass shooting that occurred, you know, really try to put an emphasis on the kind of jargons and ideologies that they use. It's not just lone wolf shooters all the time. There's a lot of specific factors that implicate a mass shooting, and all of that information is there through the posts that they make, not only right before the shooting, but they've made since the beginning of when they plan to do this. So that's what we're really looking at. We're coalescing the deep learning and machine learning aspects. Most importantly, what we're doing is my team is we're generating a new foundation for viewing mass shootings from multiple different data perspectives. It's not just about the polarization of what gun was used, or like more of the politics behind it. We want to know what compels people from the beginning, the set of different factors that compel people to commit such atrocious acts. Because I think a lot of people right now are focused on the politics of it, when there's a deep breadth of information behind it. And we can use that not only for mass shootings, but any other type of terrorist threats, right? We can look at these multiple instances, because I'm sure that there are correlations between an international terrorist threat and someone who commits a domestic mass shooting. So that's kind of what we're doing. We're building really a fortified mathematical model, so we can basically ensure the best predictions that can save our children. It's a matter of getting the right data, and it exists as long as we do it in a way that emphasizes privacy more than anything. And also looking at multiple different factors, not just going immediately into, oh, what kind of demographic the shooter was. And we're trying multiple things over and over. So this was a very cursory introduction into the type of mathematical models and techniques that you can use. But really the underlying foundation is, anytime there's a machine learning model with a small or imperfect data sets, there are multiple ways to mitigate it past just, you know, accepting it as status quo, like, oh, we can't put machine learning on this. So that's kind of what we're doing. And more importantly, we have that willpower. We have that willpower here to generate different conclusions, to look through different iterations and processes, which is why this project has been 2.5 to 3 years in the making now, because it takes a long time to procure the right data. And it takes a long time, and I know a lot of people are antsy to go to the press and media about, hey, we predicted mass shootings with like an 89% accuracy. Well, unless you truly understand what that accuracy means, what exactly you're trying to classify for the future, it's really going to end up becoming bullshit. So that's kind of what this project and this talk is really about today. It was about, hey, here's a cursory introduction into these machine learning techniques you can use if you have imperfect data sets, but moreover, understanding where exactly mass shooting data lies and how we can use it most effectively. So I'll take questions now. Sorry if I talk too fast. Go ahead.
Oh, when you're taking threat data from a purely anonymous forum, does that restrict your data to only the text itself?
It does restrict the data to text itself. So that's a really good point, actually, because when you have anonymized profile, most 8chan users, for example, don't even have a name or a photo associated with their profile. So yes, it restricts it to the text, but the way we circumvent restricting it to the text is actually understanding what the text espouses. When you're crawling through 8chan posts, you can see a thread of the post that they made previously, and that's even though it's anonymized, it provides a bigger depth and breadth into how exactly someone find a post like this on social media, decides to replicate it, decides to post more about it, decides to find people who also agree with that ideology, right? So yes, it is restricted because it's anonymized, but you can do a lot with the text itself and looking at a history of the text patterns that were posted. Because I guarantee you, for example, the Chibata Poway shooter was directly motivated or indirectly and directly motivated by the Christchurch shooting. And there are loads of information on how he like responded to the text in that forum, how he decided to create his own forum around it, and then how he decided to use the same anti-Muslim sentiment and using it in an anti-Semitic way. So there's a shit ton of information that we can use in this area. Yeah.
How would you explain machine learning, like what it is? Like
to someone who's not ML oriented? Ugh, that's a good question. Really what machine learning is it's all dependent on the user. It's not that any computer doesn't have inherently more power and it doesn't it's not like a robot that can automatically do all these cool things. It's really about what the user inputs to it. So machine learning in the most simplest way possible is training a computer, moreover training an algorithm to respond and make effective generalizations and predictions in data that can either automate what humans are already doing or provide new insights to predictions that have been made before. It's not about like the computers going off and like doing all these like insane things, which is the misconception about AI. It's really dependent on how well the user frames the data and how well at the fundamental core these machine learning models are defined by. So it's a lot more simple than what people think, and it's not just like the robots are taking over, you know? Yeah.
How can you feed other strong indicators into it, like domestic violence?
Ooh, so that's the thing. So for example, it goes back to ensembling, but ensembling in the most untraditional sense. So say we have one that just does text classifying and all of that. Another one does, for example, the decision tree model that we created has the most accuracy in identifying the location of the shooter into the occurrence of the event. So we've discovered that when the shooter is on the premises or in a playground or when they're positioned right outside of the door while people are coming out, that creates a lot more deaths than going into the individual classrooms and hunting people down and doing that. So you combine that with the history of their text classifications, the type of a weapon that they used. Again, considerably, assault rifles can do a lot more damage in few minutes than a 9mm handgun or pistol. So you combine that with that, and you kind of get a generalization. Again, there's no specific technical model that can do all of these things. It's literally a combination of different technical models. But overall, if you get enough generalizations off off of this regression model, enough generalizations off of this decision tree model, enough generalizations of this, you can basically create a report of here's the most common thing that we found throughout all these past instances. Does that make sense? Good. Really? Okay, awesome. Cool. So again, just please make sure to be in contact with me. I have Twitter and my Neveragaintech. And actually, some really cool things on another side of what Neveragaintech has done. We've gotten a lot of traction because our focus isn't just on machine learning and data. It's focused on the policy aspect. So we've written presidential policies for 3 candidates this year, some of them including Hickenlooper and Bennett. And what we did is we kind of used the data that we consolidated to create more effective policies and like what should background checks be actually instantiated by. We got a lot of traction on Forbes, Smithsonian, and we'll actually be featured in an upcoming documentary that comes out this November. It's called The Great Divide. I think it'll come to Netflix. It's about like the untraditional heroes of gun violence. So not just the activists, but the people. And I think it features Frank DeAngelis from Columbine too. And so that's what we're doing. But moreover, I think it's a really compelling cause because it's a team of young women in data science like me who are really putting their passion into it. I can't exalt my team enough. They're really the ones behind this. I'm just like a face for it, but they really were the ones. Like I was just talking to my ML model mentor the other day. Her name is Claudia Perlich, the most smartest person you'll ever meet. And she was saying that, yeah, it's hard, but because, because there's already like a, I wouldn't want to say stereotype, but because there's already a stereotype of, young women in data science, this kind of compels us to even contribute more to the cause, right? And that's why we're so much more passionate about this. So long story short, please be updated about what Neveragaintech is doing in general. There's a lot of links online that show what we're doing in the policy side, what we're doing on the social advocacy aspect. And again, if anyone has any thoughts or considerations or wants to join the team, we're rolling out a new data science team. Out of 200 people, we like selected 3 or 4 people strictly focused on the decision tree aspect of it and like creating these generalizations. So anytime you guys have any input whatsoever, want to learn more about the project, just please reach out to me. I think I put my email there too. I think that kind of summarizes it. I hope, again, I didn't talk too fast. I tend to do that when I get excited about math and machine learning. But yeah, I'm here to answer any other questions. I'll be here for a while afterwards. So thank you so much.